Hi, my name is Nicole Taggart. Thank you for joining me for this presentation. Today, we're going to talk about the influence of organism age, exposure time, and plastic pipe on microplastic ingestion by Pomacea paludosa. For a little bit of background, microplastics are defined as small pieces of plastic debris that are less than 5 millimeters in diameter. They have exploded in occurrence across aquatic environments, largely as a result of single-use plastic culture and waste management practices. At high concentrations and at such small particle size, they are ingested easily by aquatic life ranging from zooplankton to large aquatic mammals. Particles can spread across food chains easily, and microplastics have been found in the fish we eat, the water we drink, even in our sugar, salt, honey, or beer. Further, because they are by design hardy and long-lasting, the ability of microplastics to accumulate in ecosystems and organisms without biodegrading, potentially for hundreds of years, presents a considerable hazard to aquatic ecosystems. So we have to ask ourselves, what are the consequences of ingestion of microplastic particles? Consumption of microplastic particles has both a direct and indirect effect on organisms when consumed. Direct effects include digestive consequences such as decreased rate of consumption and potential starvation, as well as liver glycogen depletion, fat vacuolation, inhibition of digestive enzymes, disturbance of intestinal function, and most seriously, disturbance in growth, lifespan, and reproduction. With regards to indirect effects, microplastics have been shown to act as vectors for toxic chemicals. Contaminants are attracted to and absorb onto plastic surfaces, which cause health effects on aquatic organisms once they are consumed. Known chemicals include PCBs, PFAs, DDT. Additionally, many plastics already contain chemical additives such as flame retardants that are released into the digestive system of organisms after consumption. These effects are dependent on the number of characteristics of the microplastics consumed, including plastic shape, size, and type of plastic. Plastics can be created purposefully, like for cosmetic uses, or through physical or chemical degradation of larger plastic pieces. These are called primary and secondary microplastics, respectively. Primary microplastics include plastics such as microbeads, which have been used commercially for products like toothpastes or facial cleansers. However, secondary microplastics are much more common as a pollution threat. It is important to note that a majority of research done on microplastic pollution deals with uniform particles such as microbeads, and seen on the figure to your far side in the snail, and mostly focuses on ocean environments. In the natural environment, microplastics are present in varying sizes, shapes, and forms. Plastic fragments, fibers, and films are some of the most common forms. These particles have non-uniform and jagged edges, which may be processed differently by an organism's digestive system. This suggests that laboratory research with uniform plastic particles is not entirely environmentally relevant for risk assessment and management. This study uses real plastic particles, which are environmentally relevant. The purpose of this proposed research is to characterize the consumption and effects of non-uniform microplastics on freshwater organisms, apple snail, which is also known as Pomacea paludosa, in support of environmental risk assessment and management of plastic pollution. To this end, we developed 3 objectives for analyses. 1, did the organism's age influence plastic consumption? 2, did plastic type influence plastic consumption? And 3, did exposure time influence plastic consumption? In order to answer these 3 objectives, an experiment was developed under a factorial design in which Pomacea paludosa at 3 different ages, 3 days, 2 weeks, and 1 month, were exposed to 4 different plastics: polymethyl acrylate, which is also known as PMM, polylactic acid, which is PLA, polyethylene terephthalate, which is PET, and nylon, which is PA66. Organisms were collected at one of 8 experimental periods for a total of 96 treatments. 10 snails per replicate were exposed to the 4 given plastic types at a concentration of 1 milligram per liter. At each exposure interval, 5 replicate snails were collected. Snails were then dissected and digested. Through exposure to heat and hydrogen peroxide, the flesh of the organism was separated from the microplastics. Following this, solutions were filtered and microplastics were analyzed and counted under a microscope. So concentrations of microplastic consumed by organisms varied widely. There were extremely high counts of particles, up to 2,243 pieces of PET in a 1-month-old snail, which was possibly caused by mechanical degradation of larger particles by the snail during ingestion. In the first figure, we can see a trend of particle count within 3-day-old snails increasing from 1 hour to 3 hours before decreasing, then increasing again after 96 hours. Similarly, within 2-week-old snails, this count decreased after 3 hours, then increased after 12 hours. For 1-month-old snails, this count decreased after 6 hours and increased again after 12 hours. A pattern of increasing, decreasing, and increasing particle count was mimicked across PMM and PET exposure times, but not by PA66. This pattern suggests cyclical ingestion and excretion, and the time of decrease is slightly offset by the organism's age. This is one of our significant differences found in the study. There was a significant difference in the concentration of particles found over duration time in PMM exposed snails aged 3 days. So over the intervals of 1, 3, 6, 12, 24, 48, 72, and 96 hours, it was found that 48 hours and 24 hours and 96 hours and 24-hour counts were statistically significantly different. Similarly, in 2-week-old snails exposed to PMM, there was a significant difference between 96-hour counts and 24-hour counts. More extreme was the difference in exposure time counts by snails aged 2 weeks when exposed to PLA. These snails saw significant different counts in consumption between 96 hours and 1 hour, 96 hours and 6 hours, 96 hours and 12 hours, 96 hours and 48 hours, and 96 hours and 72 hours. Snails aged 1 month and exposed to PLA saw significant differences between 12 hours and 1 hour, 24-hour counts and 1-hour counts, 72-hour and 1-hour counts. Snails aged 2 weeks and exposed to PET had significantly different counts between 96 hours and 12 hours. Snails aged 1 month and exposed to PET had significantly different counts between 6 hours and 3 hours, 12 hours and 6 hours, and 96 hours and 6 hours. In conclusion, there was no significant difference in consumption found according to snail age, and there was no significant difference in ingestion by plastic type, but there was a significant difference in consumption over exposure time of certain snails in certain exposure times. These times were, again, PMM for 3-day-old snails and 2-week-old snails, PLA in 2-week-old snails and 1-month-old snails, and PET in 1-month-old snails. There was no significant difference in concentration of particles in PMM for 1-month-old snails, PLA for 3-day-old snails, PET for 3-day-old snails, or PA66 with snails of any age. Lastly, I want to reiterate the trend of consumption increasing after 1 hour of exposure, reaching maximums and decreasing and increasing again. This suggests a biological cycle of consumption and excretion. The results of these experiments will afford a more complete understanding of the effects of non-uniform microplastics have on aquatic environments and organisms. This research is ultimately intended to further protection against efforts of aquatic ecosystems against microplastic pollution. I want to thank you again for your time, and I welcome any questions you may have.